Okay, here are some of the learning objectives to wrap up chapter 12. There's 12.6 and some other ones. And we're going to go a little out of order here in our book, but we're going to start by identifying, in balanced equations, catalysts and intermediates. So the definitions of those, we know that a balanced equation, as we see it, tells us what happens in a reaction, but it doesn't tell us how. Sometimes it happens in two different steps. And intermediates are things that are in the middle of the reaction, and catalysts are things that we put in and then we get out at the end, but they're not necessarily going to appear in the balanced equation, but they're involved behind the scenes. So let's take a look at this. The catalyst. Catalyst is something you put in and you get back at the end. So here I've got chlorine put in step one as a reactant, and then at the end I get out the chlorine gas. So that's a catalyst. That's something I can control. I put it in, it's gone in the middle, and then we recreate it in the same quantity at the end. You'll see that those cancel out. Neither one of them appears in the balanced equation. Contrast that to the intermediate. The intermediate is something you have no control over. It forms in the middle, so in the first step, I'm making ClO, and then I'm consuming it in a second step. It cancels out also, but I did not put it in, and I did not get it back. It was there in the middle. So ClO gas is my intermediate for this reaction. And then when we try to find these mechanisms, we have to justify them by experimentally determined rate laws. And we're allowed to do this for mechanisms only. There are two criteria that must be met. If we have this balanced equation here, 2 NO2s plus F2 makes 2 NO2Fs. And we propose a mechanism. In order to say if this mechanism is likely or not, two things need to occur. One is the sum of this equation needs to match the real balanced equation. So if we add these up, we have to cancel some things out. We cancel out those F's, and then the combined we get 2 NO2s, and you need to show this and justify it, plus F2 makes 2 NO2Fs. So my first criteria checks out. This balanced equation matches. The second criteria is the rate of the slow step needs to match the experimental rate. And they're two separate things. So my slow step, my mechanism rate, has to do with the molecularity, which we said was the collisions, K, and then it's my reactants, and it's just whatever coefficients they are, because mechanism steps tell me how they collide. Those are both to the first power of the slow step. So NO2 to the first power, F2 to the first power. Since this is a mechanism, it's telling me that these two things collide with one another. That's really what the order is that we're talking about here. So K, NO2 to the first power, F2 to the first power. Does that match the experimental one? Yes, it does. They happen to be the same. So this is a pretty good bet that this is a justifiable mechanism. This experimental rate, it's worth noting, can only be retrieved from data. So we spent the whole first part of this chapter trying to get this rate law experimentally. Mechanisms are just coefficients become the orders, and they need to match in order to say whether or not your mechanism is true. The last thing we would try to do to try and prove this mechanism correct is this intermediate right here, fluorine. If we definitely want to say that this is the right mechanism, if we are able to detect the intermediate in the middle of the reaction through some experiments, then we might have a clue that this is actually what's going on. So right now we're just going to evaluate mechanisms to see if they match rate laws. So here we go. We've got an balanced equation and an experimentally determined rate law. Okay. You'll notice this does not match the coefficients of the overall reaction because this is just a summary of what's happening. But then my mechanism actually looks at the collisions that take place to see what the rate laws are. So First thing, let's add these up. Does this equal my balanced equation? So my intermediates there, I've got my n's are going to cancel out. I've got my N2O is going to cancel out. And that gives me 2 NOs plus 2 H2s creates N2 and 2 H2Os. So my first criteria is met. That is the balanced equation that we were given. My second criteria is my slow step rate law needs to match the experiment. Rate equals K. This one is NO to the first power, H2 to the first power. That one does not match my experimental, so this mechanism is probably not correct. So let's look at another variation of this. Maybe this first step is not the slow one. Maybe one of these other steps is the slow step. So here's the same mechanism, the balanced equation proposed, and now my second one is the slow step. If my rate of the slow step equals K N N O, that does not match our experimental rate law either. Our experimental rate law was rate equals K N O squared H2. Okay, but there's a problem with this one. N happens to be an intermediate. So we're not allowed to have intermediates in the rate law. So we need to get rid of N. So here's how we do that. Notice what else has changed here. This first mechanism has it's an equilibrium. This is a fast reaction and it's at equilibrium. There are equal rates going forward and backwards. We'll explore that idea later. If their rates are equal, then I am allowed to do some substitution. Watch, if I set their rate laws equal to one another, I get, for experiment 1 there, rate forward and reverse, I have a case where NO and H2 to the first power are going to be equivalent to N and H2O to the first power. That actually lets me do some substitution. If I divide both sides by the H2O, okay, those are going to cancel out. And once they cancel out, I've just solved for N. N equals NO to the first, H2 to the first over H2O. Now we can take that and substitute it back into here to see if this matches. So we do need to do some mechanism substitutions with intermediates. So if we rewrite this, we get rate equals K. Now N is going to be NO times H2. Well, I already have an NO, so I'm getting another one in there. So this is NO to the second power times H2. But this is going to be over H2O. Okay, so substituted, this is my rate law. Once I substitute that N in there, using the equilibrium in step 1. Now we can see that this doesn't match here either. So it's closer. We don't have the water in the bottom, but the top matches. So what happens is, okay, this first one is not the rate. We saw that. The second one is not the slow step. Maybe it's the third one. Now, in order to do the third one has N2O in it, which is an intermediate. So N2O, we could substitute N and NO, which N is an intermediate. So we'd have to do this like double substitution. We are not going to do that in this class, but we do need to evaluate whether or not these mechanisms will happen. So you're going to be bound to this single substitution. If you wanted to try this third one, see if this third one is the slow step, it will work out, but you need to do like substitutions inside of substitutions. But for this one, we can just say that the second step is not the slow step. Okay. Here are some objectives going forward then for the rest of the chapter in section 7. And this is where we get some kinetics of these equations, the potential energy diagrams. We've seen before that this distance here is my energy value. And it doesn't matter what the steps are or the mechanisms. That's just an energy term. Final minus initial, am I going up or down? Delta H. We're familiar with our product's energy and our reactant's energy, but a new one here is going to be the kind of our intermediate, our transition state. We're going to be interested in this point up here. And then the energy required to get up to that point, we say, is the activation energy. Because in order to get, even though my delta H is lower, which is favorable, in order to get to that lower state, we need to overcome this activation energy before we can get down here. A good example is combustion. Combustion is very favorable, exothermic. But not everything burns. You have to light a match and put some energy in to start the process, and then once you get to this transition state, then it'll proceed to the products. The transition state is its own molecule, or kind of a hybrid between two molecules where bonds are breaking and forming. And we are going to want to say, hey, the transition state, the molecule responsible for the transition state has an energy value here. The activation energy is a distance. My reactants are here, my products are here. We want to be able to graph these 5 points: reactants, products, transition state, and then the activation energy gap and the energy change gap, and read these graphs. We also get, again, Maxwell-Boltzmann curves that show us all the energy of all the particles in the sample. And remember that some are moving faster than others. So now energy is on the x-axis. So with my potential energy curve, energy was on my y-axis, and my activation energy was like a value, that distance there. Well, now it's energy on the x-axis, and my activation energy is a value there. You'll notice that some molecules have the ability to exceed that. So some of the molecules will always react. This kind of helps us explain equilibrium and incomplete reactions that don't go 100% of the way. If I have a larger percentage of molecules that can get past the activation energy, then more and more and more of them can react. But if only a couple can, then I'm going to have more reactants. We kind of think of it as these molecules that are not able to get past the activation energy stay as reactants. The ones that are going to get past are products. And you can see the area under the curve is what we're looking at. What percentage of molecules are able to do that? We can see where do I have more products or reactants in a reaction? Because not every reaction gives me the 100% of the products. But that threshold needs to be overcome. And then when we talk about catalysts, and we say catalysts lower the activation energy. So on my potential energy diagram, a catalyst might lower that gap. Okay, so there's a different path with a catalyst. Now my activation energy is smaller. It's easier to overcome. On my Maxwell-Boltzmann graph, if I have a lower activation energy, now this red line is going to shift this way. I'll put it in blue this time. Maybe now my activation energy is here. If I lowered the threshold for the reaction to occur, this is my catalyst activation energy. I now have a greater percentage of molecules that can participate. I didn't give them any more or less energy, I just moved the threshold. So we want to be able to analyze both of these graphs and compare them to one another, especially with the activation energies, to explain how lowering the activation energy can allow more products to form, because more molecules that already have that energy are then able to participate and reach the intermediate. Here's a Maxwell-Boltzmann graph of temperature. And we can just see particle distribution, how fast they're going, which is very much related to the energy that they have. So this is the molecule speed. This is one sample. all the same sample at different temperatures, and we just kind of see the distribution here. My 100 Kelvin sample has a very narrow range. All the molecules are moving at very similar speeds and they're very slow. Some of them are moving faster, that'll always be the case, but they're very narrow band here. Now imagine you grabbed that blue line and just pulled it this way. The peak has to come down as it gets wider. What that means is you get a wider distribution. So at 300 Kelvin, now I've got a much wider distribution. So the molecules, some are still moving really slow, more of them are moving fast, and there's a greater variety of those speeds. I heat it up again, the peak is coming down. That means I have fewer molecules at each speed, but I have a much wider distribution. And then at 1,000, it gets really wide, and now my particles are getting faster and faster. They're spreading out. Some are moving very fast, some are moving very slow. So the peak is the number of particles at each speed, but at higher temperatures, I get a much wider distribution because there's just so much more speed and chaos and collisions going on that they vary a little bit. Here's two temperature graphs with the activation energy. So even raising the temperature allows us to change the, to make more products, because now I've got, if I heat it up and my particles are now moving faster, they're given more energy, more of them are able to get past that activation energy threshold. So that energy threshold didn't change. This is how much energy the molecules need to react. But at a very low temperature, I only had a couple of them that were able to do that. As I heated up, I didn't change the activation energy or any of the intermediates or transition states. As I heated up, I'm allowing more molecules the energy threshold to participate in the reaction. Here are some factors then that affect the rates of reaction. Temperature is one we just talked about because it's the number of particles moving at different speeds that can get past the activation energy. And then these other things are just things that affect collisions. Concentration. If I have more stuff, I get more collisions out of them. If I have more surface area, I have more exposed particles to collide. We mentioned and looked at things where we said orientation matters, where they have to hit the right way. Sometimes if they don't hit the right way, they won't react. And then we say in the presence of a catalyst, that will speed up reactions because it actually lowers the activation energy. So this is collision theory, some of the variables that we might be asked to explain. Here are three types of catalysts that you're not going to need to explain, but these are just examples that pop up in AP standards, and they might throw something at you like this and just say, hey, it's a catalyst. Catalysts always do the same thing. They speed up reactions and they lower the activation energy. This one is an acid-base catalyst, and it's just worth knowing as a passing comment that acids and bases, molecules act differently in acidic and basic environments. So their reaction chemistry might change depending on the pH if there's an acid or a base present. Another one is called a surface catalyst, where you've got this giant surface that attracts individual particles to it. And then as it attracts those particles, it breaks them apart. And since they're just next to one another, and then they're broken apart, they start to bond and make new things, and those new things can be released. So these things wouldn't react normally, but on the surface of this substance, they can reconstitute themselves into a new molecule. So this is a catalyst that brings them together the right way and releases them back into the environment. And then the last one is the most famous type that you're probably familiar with in biology is enzymes. Enzymes bring things together, and they make an enzyme substrate complex. It's a catalyst. They have this lock and key mechanism, which really depends on molecule shapes, and they bring these two things together, and then they can bond them and then release them where they wouldn't normally make that bond all by their own. Or conversely, they can bring in the substrate and break it apart, and then release it as two separate molecules. So one by one in biochemistry, enzymes are also catalysts that lower the activation energy.